Welcome, everybody, to the Isaac Lab office hours. Very excited to have you join us here today. My wonderful co-host, Eric, aka Strainflow, is joining us as usual. Hey, Eric.
Hey, how's it going?
This is going to be a great one. So we're going to go over some announcements really quick, but just so you know what we're going to cover today. This is the Isaac Lab office hours. And as regular viewers will know, office hours are where you get to really engage fully with all the guests on our live stream. We'll take your questions, but we're also going to do a nice little show and tell. We have a very special guest here. Actually, we have three special guests here besides Eric today from NVIDIA team. We're going to be talking about deploying Isaac Lab policies in Isaac Sim.
I get this question. I hear this question all the time. And to be honest, I don't know how to do it myself. And so I'm excited for this live stream myself because I train policies in Isaac Lab, but then what do you do with it?
It's perfect. Yeah. And I feel like Isaac Sim and Isaac Lab, they're like that peanut butter and chocolate combination. They're so good together. So this is going to be a really exciting live stream. So get your questions ready. If you have any interesting projects that relate to Isaac Lab, feel free to start sharing them in the comments, not just for us, but for other people viewing. It's always great for people to learn and see what other people are doing. Let us know where you're watching from. Speaking of where you're watching from, as you can see on the screen, there's a very exciting event happening next week in Paris. GTC Paris is next week. We have been sharing the news about the live stream in the live streams about all the sessions that are going to be happening. We've been releasing some great playlists. We have a GTC channel on the Omniverse Discord server where you can also follow news and announcements there. And I'm also very excited to share that we have a community discount code, which will give you some discount from the GTC Pass, which is actually pretty affordable. It's very inexpensive, actually. And not only that, if you do happen to be going to the Viva Tech conference, your Viva Tech Pass gives you free access to GTC Paris. So we hope that anyone who's local to the Paris area, even if it's a little bit of a hike for you, you will not regret going. There's going to be an amazing keynote by Jensen, many sessions, workshops, certifications, all that and more. You can leverage that QR code on the screen right now to bring you right to the screen. We'll post some links in the comments. If you miss anything, come right over to the Discord server afterwards. We'll be glad to help you just look for that GTC channel. But we're all very excited. Some of our team is getting ready to leave headquarters to head to Paris. Very exciting. So I hope everyone out there can make it, definitely can make it. And let us know if you need help while you're there. We'll be glad to help you in that GTC channel. Another really exciting thing that's happening right after GTC Paris actually is the Robot Worldwide Hackathon. This is amazing. This is actually an in-person and a virtual hackathon. So you can take place you can join no matter where you are in the world. It's basically a great occasion to release the brand new Le Robot SO 101. So this is all revolves around the SO 101 robot. And it's being called the Robot Worldwide Hackathon 2025. We have a QR code there that'll bring you to a nice informational page. But basically, it's going to be about 30 hours or so of the hackathon. So it's going to be one big, giant robotics lab for the entire world. It's on June 14th and 15th. Like I said, it's open to all. You can register for free. And the only rule is to have fun and help each other. That's it.
And I'm not sure if it'll be here. I hope it will be in here in time, but I've got an SO 101 on its way to my house.
Amazing.
So I'm going to participate in the hackathon, and I'm going to try. I'll just start by opening up the box and see how far we can get.
Well, I think it's going to be great. So the next 2 weeks, obviously, are going to be action-packed. Follow along for all the news on the Discord server, and obviously, we'll be covering things as they happen on our blogs as well. All right, so we have a very special show today, the Isaac Lab office hours, because we're covering, as we mentioned earlier, deploying Isaac Lab policies in Isaac Sim. And as Eric just mentioned a minute ago, he's also very interested in learning this. So he's going to be asking questions as well throughout the show. Let's bring on our very special guests. We have a veteran of the live stream. So sorry, how are you doing?
Thank you all for joining. And excited to talk about Isaac Lab and Isaac Sim today.
Thank you for coming. Do you want to tell me what your role is at NVIDIA really quick?
Yep. So I'm on the tech marketing engineering team for some of our robotics platforms. So my job involves teaching developers like yourselves how to use Isaac Sim, Isaac Lab, and all the cool things that our robotics platform includes.
Yeah, and she's super helpful as a marketing team. So the information you're getting about all the technology, it's because of people like Asari that help put that together and publish it. So thank you so much for helping educate the community. Speaking of which, we have another great contributor here. This is Sean with the great spelling of Sean here. Hey, Sean.
Hey, Edmar. How you doing?
So, it's great to see you. So tell me what's your role at NVIDIA?
Okay, I'm also a technical marketing engineer, just like Asawari right here. We work on teaching developers, showing you guys how to use Isaac Lab, Isaac Sim, making all these things known to you guys. Just happy to be here.
Amazing. Well, we're grateful for your presence. Really appreciate all the hard work you guys do every day. We have our final special guest, Stephen. Stephen, how are you doing?
Hi, hello, Sean. Hello, Edward. Hello, everyone. My name is Stephen. I'm a robotic systems engineer on the Isaac Sim team. A lot of my work involves with building digital twins as well as different simulation workflows to enable all kind of amazing things that you guys do.
That's amazing. Okay, so we are really excited for today. So like I said earlier, this office hours is meant for everybody to come and ask your questions. We have a dream team here able to help. I can't even tell you how much I've seen in terms of the growth in the community of robotics developers, people leveraging Isaac Sim and Isaac Lab. Every week, we see more and more people jumping onto the Omniverse Discord server, jumping into the Isaac Sim channel, Isaac Lab channel. There's so much engagement, so many fun projects across LinkedIn. I highly recommend LinkedIn. Following some of the developers here even. Stephen actually just did a nice post on today's office hours on LinkedIn, so I highly recommend you follow Stephen. Okay, so let's get started. So why don't we start just really quick with like what is a policy? So for people who might not be aware what a policy is, and we should also cover really quick like what's the difference between Isaac Sim and Isaac Lab, and then I know we're going to get much deeper into things. But for a high level view, who wants to take the first question about what is a policy?
I guess I can take the question. So a policy is a neural network. It takes in a series of inputs, goes through a black box, does some magic, and it spills out some outputs. The input, we call it observation. It could be a set of parameters that you set, and the output could be robot control actions. It could be really anything. And then we want to essentially translate that action into control parameters to control the robot. And,
okay, awesome. Go ahead.
Oh, and one more thing. And compared to classical control methods, such as like optimization control, a policy could explore more action spaces, so it can give you more natural actions, and it can make it much easier to control more complicated robots, like a humanoid, for example.
Very powerful. Okay, so how do we want to define Isaac Sim and Isaac Lab, and why is it really kind of important to learn how to deploy Isaac Lab policies in Isaac Sim?
That's actually a great question. So Isaac Lab is primarily focused on performance. So the goal of Isaac Lab is to simulate a lot of robots all at once on a computer. So you can imagine we're going to sacrifice on some quality of the data. We're going to take some shortcuts by giving ground truth data and all of that. Isaac Sim, the focus is on simulating fewer robots, but in a more sophisticated environment. So it can give you more realistic data. So this way, you can try to bridge that closing on that sim to real gap a little bit by using Isaac Sim, deploying the policy, testing Isaac Sim before you deploy on your real life robot.
Fantastic. Okay, cool. That is super.
Sometimes the way I think of it is that Isaac Sim is a world simulator, and Isaac Lab can orchestrate multiple simulations and different training methods for policies.
Exactly. Yeah. That's absolutely right. Yeah.
Okay, great. All right. So, Stephen, I know you prepared actually a nice presentation. Did you want to start with that?
Oh, sure. Let's start with that.
Okay. So I'm going to add your presentation to the screen here. And
okay.
I think, yep, we got it.
Awesome. I'll just put it in the regular viewer so we can switch between the presentation and different tabs that we're going to reference to. So welcome to our office hour. We're going to talk about how to deploy policies in Isaac Sim. We're going to focus on Isaac Lab policies, but really I think the ideas translates across different policies from different simulators as well. So my name is Stephen. I'm a robotic systems engineer. Join me are Asawahi and Sam from the marketing team, and they're going to help us answer all the questions. In terms of agenda items, we're going to talk about a few things. First of all, we're going to talk about the Isaac Lab environment parameters. So we want to try to understand what are the requirements for an Isaac Lab policy. And then we're going to talk about the Isaac Sim's policy controller class that we wrote in Isaac Sim. This is a class that can load your policy, it can parse the parameter file, and it can really automate a lot of the process for you, so you can deploy a policy faster in Isaac Sim without using as much code. And then we're going to have a little activity trying to configure the robot and the simulation environment together for the H1 robot. So this is for the case where if you want to deploy a policy using ROS, where you cannot leverage the policy controller class and have to do some of that setup manually. If we have time, we want to talk about how to do that setup. And in the future, we could talk about how to deploy your policy using ROS and interface that with Isaac Sim as well. So great question from Admar. This was a question, why use Isaac Sim? So first of all, so like I mentioned before, Isaac Sim is designed for multi-robot, multi-workflow simulation, like what Eric mentioned. And Isaac Sim can provide you with realistic sensor model. So not only we can give you realistic, for example, LiDAR camera data, but we can also accurate data, but we can also give you realistic data where it has all the distortions that you expect from a real life camera, all the flaws that you expect from a real life camera. So to bridge that sim to real gap. In Isaac Sim, because we're simulating fewer robots compared to Isaac Lab, we're simulating thousands during training, we can also give you higher fidelity robot meshes that are closer to the real life robot. And finally, we have built-in support with ROS, with Replicator, with Spatial SDG, and other custom Omniverse extensions, so we can test more workflows with your policy as well. And doing it with Isaac Sim can help you reduce that sim to real gap. You can also test it in more complex environments, such as with other robots, manipulators, other humans even. And also it can validate in more complex environments that we provide, such as warehouses, offices, and hospitals, and so on. So let's talk about how to run a policy. Like we mentioned before, at its core, it's just you give it some inputs, we call it observations, into a neural network, and an action comes out, and that's the output. But there's more intricacy than that. So first of all, how do we get the observations? Well, in Isaac Sim, there are a few sources. You can get it from sensor, so that's camera, LiDAR, IMU, contact sensor. You can get it from the environment. So in our Isaac Sim, we have the articulation class, where it can give you robots for the global position, its orientation, joint parameters, such as joint position, joint effort. And then the third sort of input could be your command. So if you're telling the robot to move forward, that could also be an input we pass into observation. So the policy will try to move the robot to move forward, and and so on. In terms of action, this is again also specified by the controller. Most of the controllers in Isaac Sim, in Isaac Lab, will give you position output. So give the robot a target position that will try to move to. But it can also come in other forms, such as position control, velocity control. Tell the joints to move at a certain speed, effort control to apply a certain amount of force or torque on a joint. And one thing I want to note here, which is not really an output, but it's the joint order, because oftentimes we see errors because the joint order as the controller output doesn't match with the joint order that the USD or the robot expects. So sometimes there may be some mismatch. So that's also something we have to take care of as well.
So really, it's you've got just the observations are these raw numerical inputs to a neural network, and you have to kind of interpret and figure out what which API calls, if you will, you'll feed into the neural network, and then you'll get these actions that are once again these raw numerical kind of 0 to 1 neural network outputs, and then you have to interpret, okay, what am I going to do with those the kind of that raw output? Is that right?
That's right, yes.
And is that this whole big thing, including the interpretations, is that all part of the policy, or is just the neural network the policy, and then the other parts are called something else?
Just the neural network. So only this part here is the policy. Everything else are stuff we had to prepare. So we had to piece together all the sensor data, all these individual pieces into an observation, which is a big tensor that the neural network expects. And then the neural network spit out a big tensor, we can call it action. And then we had to figure out how to take that action and then configure it into the individual pieces that the robot wants.
And those ends, like the interpretation that we do or the tensor preparation, those are outside the policy.
those are outside the policy, and that will be our focus today. And
Okay, all right. Well,
yeah.
is it, I've been trading some stuff in Isaac Lab,
Mhm.
and I use all this privileged state information
Mhm.
to train my policy, and I know that I'm painting myself into a corner because once I get to the real world, I won't have those sensors anymore, and or
That's
I won't
right.
have that privileged state information. All I will
Mhm.
have are the actual sensors on the robot, and so
Right.
I'm really interested in that whole kind of process, if you will.
Yeah. So I think an example I could give you is in Isaac Lab policies, they require stuff like robot base velocity or robot positions. In Isaac Lab, we just call the articulation API, and then we can get, okay,
Yeah.
now the robot's moving forward at 2 meters per second, but we don't quite get that data. You don't quite get that data in real life. The way you would do is you have to attach an IMU, inertial measurement unit, to the robot. That measurement unit can give you linear acceleration data, and then you have to compute the velocity from that linear acceleration and do some frame transformation to make sure that match with the simulator. When we're running the ROS example, that will be released in ISAC 5.0 for deploying policies. We also try to mimic the real life behavior as much as possible by using simulated IMUs. And we realize that putting the IMU in the wrong position or wrong orientation can have a big impact on how the policy will end up running. So a lot of that frame transformation and making sure data matches is critical for running your policy and deploying and doing this into real deployment.
Well, this is all very timely because I know we have a lot of people in the community who, like me, have made it to that point of, they can train something to work in Isaac Lab, but now they're wondering, well, how do I deploy that to Isaac Sim, or how do I get it to actually work in the real world?
Yeah.
In fact, I do see a question right now, quick interruption. But the question basically says that in today's tutorial, we're going to show for the H1, right? But could we also show a similar example for the G1? Because this user is having some issues with it, wherein it works perfectly in lab, but then not when you go from lab to sim. So I think this question is more, I think this is something, of course, that we'll be aiming to help with through documentation. So with every new release, we'll have some more examples for different robots. And the idea is that those tutorials help you at least give some tips and tricks to get started, and useful debugging tips as well. So no matter what form that or robot form you may be trying for, if there are some issues, hopefully debugging tricks are the same. And then, of course, for further issues, we have the Isaac Sim forum and the GitHub itself, where you can post more logs, details of exactly what you're trying, why it isn't working. And the community is very helpful, and engineers also are very helpful in just answering those questions very specifically to your use case.
Yeah. Okay. Yeah, so we'll just go to the next slide, which I think might answer some of the question as well. So sometimes your observation and your actions might be matching. One of the reasons why your robot may not work is because the simulation setting and the physics settings are not exactly aligned. So that could be whether if you're using CPU physics versus GPU physics, if you're running at the correct physics step, and so on. So not only we have to make sure our robots match, observations match, action match, but also this general simulation settings and physics settings also match, which should be helpful for debugging your case as well. So we'll talk about general steps on how to do this. And the first thing is we have to configure a robot. So the UST Timing Isaac Sim, they have default parameters for the robots, joints such as stiffness, damping, maximum velocity, and maximum effort. These might be different from what your controller expects. So Isaac Lab has this whole environment configuration. So we have to make sure our robot matches with that. The other thing is the default position. So a robot in Isaac Sim, the default position will be all the joints, will have default position of 0, whereas Isaac Lab might expect a different value as well. So we are going to talk about later in today's tutorial, office hour, on how to bake those default positions into the robot. And then the next thing is we have to set up a simulation environment to make sure where the physics settings, the simulation settings match exactly as what Isaac Lab does. And then during runtime, there are two different workflows. One is we can do everything in Isaac Sim. We can compute observation, we can compute actions, and then we just apply the actions at runtime. But you may also choose to use ROS instead as an intermediate term. So this way you can easily convert your ROS node that does all the policy stuff to a real life robot easier. So in that case, in ASIC-Sim, we want to publish our data to ROS, and I have a ROS node that takes in those data, process it, turn it into an observation, and then compute the action from it, and then send the action back to ASIC-Sim, where we interpret that action and then apply it to the robot so we can move or walk at a pace we expect. So today we're going to talk about the top line mainly. And then for the ROS related workflows, we can talk about it in a future office hour, or if we have time, we can briefly glance over it as well. So
basically, there's kind of an easier way we can deploy these models to ASIC-Sim to test them in ASIC-Sim, but that wouldn't directly translate to the real world.
That's right. So
or we can go through ROS, which is a little more work, but then we can transfer it to the real world.
That's right, yes. Doing it through, there are advantages and disadvantages to both methods. Like Eric mentioned, doing through ROS can help us transfer to real world easier. But again, you're also seeing you might be hitting other issues such as latency. If a ROS node is publishing at a slower rate than expected, then your policy may fall over, and it's really hard to debug to why. So one way we do it internally is also we first deploy an ASIC-Sim, so we can make sure the ground truth data we get from Sim matches with lab exactly, so the robot can at least walk. And then we go from there and then deploy to ROS. So it's sort of doing it step by step, so we can isolate what are the problems one step at a time.
You might even add some latency in the ROS, because I had someone ask just the other day how to simulate latency, and I wasn't sure how to simulate that directly in ASIC-Sim, but I think it'd be pretty easy in ASIC Lab, or in ROS, I mean, to just add like some kind of randomized or simulated latency.
For sure, yeah. In Sim, there are definitely ways you can simulate as well. But ROS,
you do that? Is that something you would do, or would you just not worry about it until you're working with ROS?
Usually until you're working with ROS.
Yeah, that makes sense.
Yeah. Okay. So let's maybe first talk about the ASIC Lab environment parameters. So we have a documentation that's already public for deploying policies in the ASIC-Sim, which is this one here. It's in ASIC-Sim 5.0, and it'll also be 4.5, and also be there for 5.0 as well. So if you train a policy in ASIC Lab, you get a parameter that looks sort of like this. It gives you a lot of information about the policy and the environment that it's trained in. So we'll just walk through how to read and understand this, so you can also apply the same settings to a robot in ASIC-Sim. So the first one that's important is this information here, which is the physics scene setting. So this DT is how often you run a physics step, which is 0.005 second. So that translates to about 200 hertz. Or we use this documentation. It has this exact same file. The other one that's important is a render interval. This is how often we render a frame for every physics step. If you render more often than this, then you see a robot probably simulate at a slower rate, but more continuous rendering. If you set it higher, the robot will you see more movements between frames, and it will typically move faster as well. The next one is robot setup. This is in the init state.
When I install ASIC-Sim, I download the binaries and I unpack them on my computer. Are these settings files in the ASIC-Sim installation? Is that where I would find these?
Oh no, that's a great question you asked.
I don't even. Where would I find these files?
Okay,
so go ahead.
Oh, sorry. So basically, the way to find it is you have to first train a policy in ASIC Lab. So these files are specific to the policy you train. So you want to first train ASIC Lab, and then after you export it, ASIC Lab will provide you these YAML files. And then we have to go through the.
After I export it, so usually when I train a policy in ASIC Lab, I just end up with like I forget the extension, but I end up with like a policy file, just like a single file. I haven't seen all these settings you're talking about.
I see. So yes, if you just train it using this command /train, you get a single file for the PT file. That's the
There we go,
PyTorch
yeah.
file that stores the policy. And then if you run the play.py file
Right.
instead, then it will generate you 3 more files: an exported policy file that contains all the parameters, not just a snapshot. It will give you the environment file, which tells you all about the policy, and it'll give you a third one, which is the agent file that tells you about the structure of the neural network. So how many layers, what kind of thing you train it on, and so on.
And so, will those be in the same directory as the PT file?
They'll
Or
be
in
in
a
a
different directory?
slightly different directory. So I think PT file will be in your logs, RSLRL, task name, time, and then / I think
Yeah,
exported
that
.pt.
looks right.
Yeah. So in these ones, there will be in logs, RSLRL, task, time, parameter, and then you see the agent YAML and the environment YAML there.
I see. Okay.
Yeah, these are really important because it tells you how to interpret the policy. Otherwise, if you only have the policy, it's really just a binary file, and there's no way to understand, what the policy expects and what it outputs. So the first part is to set up physics. The second part is about setting up the robot, and the important part is actually this part right here. So this tells you the default robot position. As in the policy, is the control action is based on default plus the control action times an action scale. So you have to know what the default position is before you can know what's the absolute position to apply to the robot. The other important part is this is where the policy expects the robot to start from. So by default, our robot will start at 0, 0 position for every single joint. So we'll have to first set it to this position before we can start the simulation. Otherwise, the policy may not work as expected.
And this seems really similar to the default state in the robot configuration file we use in Isaac Lab.
Yes, this is where you set it. So the robot configuration state is where we will set this information. And then here they're just porting that information over.
Okay, so it should be like the same. It should be grabbing these values from that file.
Exactly. Yeah.
Okay.
They should be the exact same values.
Yeah. Quick one. So how do we determine the physics, the parameters between Isaac Sim and Isaac Lab if they're matching or correlating? How would be a good way to determine that?
How do we make sure the physics parameters are matching?
Yeah, between Sim and Lab.
That's a good question. So for Sim, the physics parameters are stored in an object called the physics scene. You can go in there, you can set the GPU physics and all the parameters and make sure those match with Isaac Lab. You can find the physics parameters here in the physics section, and you can go through each of these parameters and make sure they match with what you have in Sim. And for additional physics parameters, such as like on the robot side, we are going to talk about that in the next section.
Okay.
Yeah. So the next part we're going to talk about is the actuators, which are the joints. In Isaac Lab, they specify like this. So they tell you which joint names to look at. Effort limit is how much force the maximum amount of force that you can apply to a joint. Velocity limit is the maximum speed you can apply to a joint. Stiffness, you can think of this as, so if you have a PD controller, stiffness is the proportional part, the KP constant. So your total effort will be computed as stiffness times the delta P plus damping times the delta velocity. So that's the stiffness and damping parameters. Amateur is a motor parameter, and friction is also a motor parameter as well. So if it's none, then Isaac Sim, you just set it at 0. If it's a non-zero value, you just copy it over to Isaac Sim. One thing to keep in mind with all of these is that in the environment file here, all the data is outputted in radian. So for example, the velocity limit is in radian per second, whereas in Isaac Sim, if you edit it through USD, per the USD standard, everything is in degrees. So you have to convert velocity here to times 180 divided by pi to figure out what the corresponding degree per second is. For stiffness and damping, the unit of these are it's in they use inverse of radian, so so conversion will be slightly different as well, which we'll talk.
In Omniverse, it'll be inverse of degrees once again.
Yes, in Omniverse, everything is in degrees. So we will talk about it in this tutorial here. So here's the equation you have to use. Stiffness is kg meter squared divided by degrees times second squared, and damping is kg meter squared divided by degrees times second. So to convert it from degree to radian, you have to actually do or radian to degree, you have to do pi over 180, which is the opposite of what people usually think it should be. Okay.
Right.
Yeah. The next part is,
I've seen people have trouble with that on the forums. The
yes,
degree radian thing.
Yeah. So this is definitely one of the confusing part, and we see a lot of this on the forums. So we want to really highlight this in the office hour. The next part I want to talk about, which is also really important, is the observation. So let me pull up the observation parameter over here, and then we can just go through them together. So this is the observation for the H1 flat terrain policy. So it expects a few things from us. The first one is the base linear velocity, so how fast the robot is moving forward, left, right, and so on in a linear way.
This specific example, you can have pretty much whatever observations you want, really. Is that right?
Yeah, that is correct. Yes, you can have any observation you want. You can put a camera there, camera feed there. You want to, if you want to. Yeah. So, but this one, in this example, they're just using really basic linear velocity, angular velocity, and so on. The main thing is we have to understand how to read it and make sure when you're passing the observation tensor, the observation terms you pass in, the size had to match with what your policy expects, and the order had to match.
And the shape.
And the shape, yeah. So imagine if you pass in angular velocity first and then linear velocity second, then the policy will be confused because it would think the robot is constantly turning when it's just going forward.
Yeah, I tell you, when I was writing my the direct environment I've been working with, when I was writing it,
yeah,
I got so confused with the tensors, and what saved me was I actually used an LLM and would ask it questions about my tensor shapes. Like I would say, I've got this tensor, then I've got this tensor, and I need to add them or whatever I need to do, and it would give me some really great sample code that helped me work my way through that tensor math, which is, it's hard, but
it's brutal, yeah. Yeah, we can show you this is the observation tensor we have for the H1 flat terrain as well. So you see, we had to sort of figure out, okay, 0 to 3 is the linear velocity, and then 3 to 6 angular. We had to sort of compute it ourselves and try to make sure everything lines up. So it is a bit tricky to do, and this is something we're trying to improve the user experience as well on the ID lab side and the sim side as well. So after you figure out what the terms are, so linear velocity, angular velocity, this is projected gravity. So what's the gravity on local frame, essentially? Command is your user command. So when you go forward, left, right, joint position is where our joint positions are relative to the default position. Joint velocity, and then action, which is the previous action you put into the policy. And the next one we need to look at is the action.
So one question, Stephen, before we move on to the action.
Okay.
Let me put the question up here. It's from Sanjana. It says the ENB config defines an initial joint state, right, for the robot.
Yes.
Should the real robot be set to that initial position before you deploy the policy? Because they're noticing trajectory timestamp errors when these aren't synced.
Yes. The way you can do it is, we can show it in a later example as well. But if you were to set the target position to your USD directly and hit play, you see in the very beginning, the robot will try to move towards the target position or the default position, but it won't actually be at the default position. So in the last part of today's tutorial, we're actually going to talk about how we can bake those joint states and joint values into the robot so we can start at the default position instead of the 0 position. Okay.
That's great.
Yeah. Okay, so now for the action part. Action part is just the output from the robot. The really important thing we want to note is sometimes the robot may not have control actions for every single joint, so they will specify which joints are used for the action. The other one is the scale. So oftentimes we'll put a scaling on the robot action parameter. Again, this is something you specify in your policy. So if you specify a scale for your policy, when you're deploying Isaac Sim, make sure you also apply the same scaling to your output from the action as well.
Because the outputs from the policy will always be from 0 to 1. Is that right? Or is it from -1 to 1? They're normalized in some way.
Sometimes they could be normalized depending on how you specify it. Sometimes it could just be actions, like it could be any number, just a target position that it wants the robot to go to. Divide by a scale, I guess. So you have to apply that. So whatever the output is, multiply by a scale, and then do some additional math. I think for the H1 policy, the way we process the scale is, yes, it's like this. The action we apply is the default position plus the action that we get from the policy times the action scale. So it really depends on how you set up the policy yourself.
Okay.
Okay.
Is this in a managed environment?
This is a managed environment, yes. But if you were to, for example, normalize your policy action to 0 to 1, then when you're applying the action, you just have to remember that articulation action will expect basically a degree in radian, a joint position in radian. So you have to just convert it to whatever that joint position is in radian before you set it to a robot. So it's an additional translation layer you have to do. And then the next part is rewards. This is how, this is for training, so it's unrelated to us. And the very last part is the command. So this tells you what's the limit that the policy is designed to do. So in this case, the robot is designed to move forward from 0 meters, standing still, to 1 meter per second, just moving forward 1 meter per second. It's designed to turn at -1 radian to 1 radian, and it can do any heading. So in this case, if you're trying to give the H1 robot a command to move backward, you see the robot quickly falls over. Or if you give it a linear velocity higher than 1, then the robot is also at risk of tipping over and as well. So that sort of went over how the actions work. So the next part we'll talk about how our policy control class can help you with this. And I linked 2 docs here. One is the examples we have in Isaac Sim, and the other one is deploying policy in Isaac Sim doc. So this is the doc that we just went through, and the later part we'll talk about the different parts of the policy control class. And then in this documentation, we link all the examples we have in Isaac Sim. So the first one is on running a policy. So we actually give you an example on how to run one of these policies. So here we have is Isaac Sim 4.5. If you go to Window, Examples, Robotic Example, you see a pop-up at the bottom that says Robotics Example here. And if you navigate to the policy section, you can see there are 2 examples here. One is for the Unistream H1 robot. The other one is for the quadruped robot, the Boston Dynamic quadruped. So you just left-click on humanoid, click Load. It'll take a few seconds if it's your first time. And then you see a H1 robot walking. And you can control this robot using arrow keys, so going forward, turning left, turning right, and so on. We also have an example for the standalone workflow.
This example comes with Isaac Sim, right?
Yes, this example is shipped with Isaac Sim. We also have one for the quadruped for the Boston Dynamic spot. If you just load it in, you can also just move forward. This one can actually move side to side like this and backward. And you can control and make it turn and walk around as well. And these are shipped with Isaac Sim. Just go to Window, Robot Examples, and then you can find them here at the bottom. We also have one more workflow in Isaac Sim. It's called the standalone workflow. So it looks something like this. So my browser just froze for a second. What this workflow does is that it's a Python script you can just run directly, and it'll spawn a world for you based on the physics parameters. and then it will spawn in the robot, and it will run the simulation directly from Python. So this way you can have a closer look at how we instantiate the policy, how we initialize the articulation and all the intricacies to run policy in ASIC-Sim. So in this example, we're running 5 H1 robots with a predetermined command. Okay. So regarding the actual policy controller, what we are trying to do is this. We're trying to automate how you configure a robot and setting up the environment, because these are usually the most tedious part. You can imagine for a H1 robot, it only has 19 joints. So setting the default position for 19 joints may not be as hectic. But if you want a more complex robot, for example, like the agility robot, then a robot like that will have 50 joints, and setting the default position for 50 joints will become quite cumbersome. And then for robots that have hands that have 30, 40 more joints, is very easy to make mistakes. So for the policy controller class, what we are trying to do is to parse the Isaac Lab environment for you directly, and we'll and through API calls, we'll set it in, set the environment and the robot in Isaac Sim, so you can ignore the first 2 steps, which is configure the robot and load policy. And all you have to do then is at runtime to set up the observation, the action, and also how you want to apply the action itself. And you can look into how our API docs, how our code works through this section here, where we walk through the constructor, the load policy, and the different functions we have. And there's also another case where, okay, what if my policy gives me position output, but I want to give a robot effort control instead? Then there's also additional class you can also load in additional policies, such as in this case, LSTM network for the animal robot. And what it does is I can convert position control into torque. So this way you can apply torque to the robot directly. One more thing I want to share with the policy control class is debugging tips. So as we're writing this, we run into a lot of errors. So for example, sometimes you can see the robot is just not working at all. And this might be because the robot's joint orders are wrong. So imagine if in your policy, you expect the robot to go front leg, back leg, front left, front right, back left for the different legs, but the robot expects it in different order, then of course the control will get mixed up, and then the robot will not function as expected.
So the surprises me a little bit, because if you're using the same asset to train an Isaac lab and then deploying to control the same asset in Isaac Sim, why would the joint order not be correct?
Well, in this case, it will be, but sometimes you might be using policies that were trained a long time ago using a slightly different variant of the same asset. Then in that case, it might not work the same way. Or in another scenario, let's say in your Isaac Lab robot, it has 12 revolute joints, just like this one, but you also give it a few additional fixed joints to mount additional sensors. Then the additional fixed joints will also change up your robot's articulation tree, and also change up your joint orders as well. So in that case, you may also have to double check and make sure you are passing in the joint order in the way that the Isaac Sim robot expects it.
Got it. But essentially, if you have a flailing robot, it's a pretty good chance that your joint order is wrong.
For sure. So this should be the first thing you check. Yeah. And to check is very simple. You just spawn the robot's articulation, and then you run the prim.dof names, and this will print you the exact joint order that your robot expects. And then you go to your Isaac Lab side, and you want to make sure your policy also gives you the data in the same order.
And you might need to take that action tensor, and let's say you've added a few fixed joints. You might need to pad it at the correct indices to add some zeros to make everything match up.
For sure, yeah. Or you can take your action tensor and you just scramble the order again yourself, through code.
Sure.
Just make sure you match. And as you can imagine, like there's a reason we have all these screenshots, because these are all the issues I've personally run into. So otherwise we wouldn't have these screenshots. So yeah, the first one is joint order. The second one is default joint position. So this one, It's doing a moonwalk, and it's doing a moonwalk because the ankle joints are supposed to be set. I forgot if it's positive 50 or negative 50, but I did the opposite of what it's supposed to do. So the robot has such a hard time trying to stand up because its default positions are just wrong, and everything it's trying to do, we're adding an additional like 30 degrees to the output. The next one is the joint properties. So this is the stiffness and damping value. If you give it too high stiffness, it might overreact. If you give it too low, it might underreact. So you can see, if you remember in the Unitary, in the spot robot, like this one here, it's supposed to move the legs up quite a bit. But if your stiffness is really low, it may not have the energy to move it up as much. So you have underactuated movement.
Now the stiffness is going to tend to essentially return the joint to its default position. If you just don't do anything with that joint, it would, with some force, kind of spring back towards its default position.
That's right.
Do the actual robots, do they just have springs in the legs to do that?
I think that for that you had to look at the robot
Depends
itself.
on the robot, yeah. But it's not uncommon. It's not. I guess it must not be uncommon for the actuators on the actual robots to have some kind of a stiffness value, huh?
That makes a lot of sense, yes. Because, like, for example, a lot of actuators themselves, they'll have resistance. So if you give it mechanical movements, it will turn to electricity. So they'll have resistance for sure. And sometimes
that would be the damping, right? That would be the damping, where if you're moving it, there's some kind of a resistance.
Yeah.
But a stiffness is actually, if you move a joint and take off the electrical signal, it would return to its initial position.
Initial position, yeah. In this case, when we were moving it, you can almost think of it as your target position is where that neutral position for its stiffness is, and then it's trying to pull the robot towards the target position you're setting it to. If your stiffness is too low, it won't quite.
Oh,
right, with the stiffness.
So it's not. So the stiffness is not a value that's necessarily trying to always return it to its initial position. It's more of a value of like the torque with which. So if you give it a desired position, it kind of gives you the torque with which that actual actuator.
Right. Yeah. So it will actually try to pull it towards the target position you want to give it.
With that torque.
Right. Absolutely. So yeah.
I'll have to think about that a little bit.
Yeah.
Because it seems like the stiffness value would have a higher torque the further away the joint was from the desired position, but it must not work. Maybe.
It does. So because it's it's a PD controller, right? So how much torque is your stiffness times the delta P. So if your delta P is very far away, then it will have more torque. But remember, the joints are also limited by the max effort. So there's only so much it can give out.
Oh, I see.
Right. Yeah.
Okay.
So it does flatten out.
Got it.
It also has a maximum velocity parameter too, so it will make sure it doesn't go too fast from the higher torque. So in this case, we are giving it too high of a stiffness. So when you give a position target, it goes there instantly. So you see this shaking. And there's also stuff where if your physics scene is not set up correctly, then your robot will also just fall over because sometimes we need more physics fidelity for a robot to run correctly. So these are all the things you can try to verify, make sure everything matches for your robot. So we have around 10 minutes. Okay, that should be enough time to go over the last part here, which is how to configure a robot and simulation environment. So I have...
Could we, Stephen, maybe take one or two questions just so that we don't run out of time for questions, and then we can jump into this part. Yep, so let me share them on the screen here. The context is that in the documentation on deploying policies in Isaac Sim, the RSL RL trained policies used along with the agent and environment files. And then the question is, however, when I tried using a trained policy, it didn't work due to the model not loading errors. Is SKRL not compatible for this workflow?
The short answer is yes. The longer answer is, so for the reason why RSL works is that when you export a policy, it stores all the policy parameters, all the constants, all the weights and everything inside the PT file itself. So we can just load it directly and it will work. But if you use SKRL and other frameworks like RL games, they only give you iteration snapshots, but not quite the full neural network information. So when you run it, you might get into different errors such as I think like constants not found or whatever, and so on. There is no easy way. Yeah.
So
go ahead.
And I think really, I know Lychee pretty well, and
Mm-hmm.
I think that really what we're trying to get at is what should we be using here? Should we be using RSL RL? Is that what you would recommend?
Yes. So the recommendation is to use RSL-RL for the workflow for now, and in the future we're just going to try to add support to the other frameworks in Isaac Lab as well. But
yeah, and that makes sense because in some samples we've been working on with the community, we started off in RL games,
mm-hmm.
and we ran into some roadblocks, and so we tried switching to RSL RL and to SKRL,
mm-hmm.
and we found that it was a direct kind of just switching over to SKRL worked fine.
Mm-hmm.
It would train fine, but I think now he's having some deployment trouble. So I think we'll probably have to circle back and change to
mm-hmm.
RSL RL.
Yeah.
Even though there'll be some tweaks we'll have to make to get that to work.
Yeah.
Yeah. Okay.
Mm-hmm. Okay. Cool. Do we have more questions?
Lots of yes.
Okay.
Have some questions, yes. But if you want to finish this part, we can do the questions after it.
Sure. Okay. This part we'll keep it really simple because I think people asked about this part in the earlier section of the lab as well. So we just want to quickly go over it. We'll do it for one joint, and then the rest we can do it later. So essentially, or I'll just explain the concept itself. So let me just add a quick fixed joint to the pelvis so the robot doesn't fall over when we start a simulation. Sorry, create physics joint, fixed joint. Okay, so if you start a simulation, you see a robot is like this, but this is not quite matching the default position of what we expect the H1 to be. So let's say we want to move the leg up to 90 degrees. If you go to the joint section, and let's say let's try to find a leg, hip pitch. If we say set this to target position is, let's say 90, then if you press play, you see it moving back to 90, or I guess in our case, negative 90.
You enable
we'll see it
mode on the torso or something to make it not fall down.
Oh, yes, we added a fixed joint to pelvis, or torso works too.
Oh, I see.
Yeah.
That's right.
Okay, so did we change this joint? No. Left. Let me try to find a joint again. Left hip pitch. Okay, so you can see when you start a simulation, it tries to move to 90, which is not quite what we want. We want to actually bake the data into the simulator itself. So the way you can do it is go to Edit, Preferences, and we want to just uncheck this Reset Simulation on Stop. So if you uncheck this part, then when you stop the simulation, it will stay in this position. And you can see the position is being stored in the joint state angular part. So here's the joint position. Then when you save the file and you enable Reset Simulation on Stop again, you realize that the robot will start in this default state. So you can do this for every single joint, and then eventually your robot will match the rig position as well. I think we have it saved somewhere as well. Let me find it.
So to recap, you basically open the robot, add that fixed joint so that doesn't fall when you start running the simulation, and then you could hand set each of those joint positions, run the simulation so that it moves to those positions, uncheck that box and stop, and then you could delete that fixed joint.
For sure, yeah. Great summary, thank you. And the whole process will also be released as a part of the Isaac Sim 5.0 documentation. It will be called Tutorial 13, Rigging a Legged Robot for Locomotion Policy, where the first part we're once again talking about how to read the initial robot position, and then we're going to talk about how you can change the settings to move the robot to the default position. And then the second part, we're going to talk about how to set the stiffness and damping values to the robot so that it will behave exactly the same way as lab, and then we'll finish up by verifying and make sure the values you see on the sim side matches with your parameters on the lab side. So stay tuned for our 5.1 documentation. We are including a lot more examples for both rigging a robot for learning as well as running reinforcement learning policies using ROS and Isaac Sim.
Cool.
Okay, so
yeah, I can't wait.
yeah. So yes, time for some Q&As, questions.
Awesome. I see a lot of questions, so we can just start putting some up on the screen.
Yeah.
Let's see.
We don't have a model for in our asset browser yet. I'm not quite sure if there's any plans to release them with 5.4 with 5.0, but in the future we may try to work with the manufacturer to release more robots and more assets into go along with Isaac Sim.
And I guess in general, so the next part of the question was, is there a simple way to include a VLM to judge movements in the simulation training? Maybe this is something you could try, right? Like even developers can kind of try doing that. I don't know if do we have any examples right now?
I don't think we have any examples right now. And I think this is more of an Isaac Lab question than Isaac Sim, I think, yeah. So definitely ask the Isaac Lab forum or Isaac Sim forum, and we'll try to direct you some help as well.
On Isaac Lab, it would be in the GitHub issues. It's where your best place to get help. Mm-hmm. And for Isaac Sim, it's in the forum. But yeah.
Awesome. Right now. This is more of a comment than a question, but I think it's mainly about the AVP. I think the Apple Vision Pro example that we have for imitation learning. So we do have a tutorial, some documentation on the Isaac Lab website. But I think we could also do a blog post. We do have maybe one or two around this topic and some learning content on the Deep Learning Institute, DLI. So these are some good resources. I'll share some of the links in the chat right now.
I think we're also getting a lot of interest from a similar interest with the Groot. And so like, how could you use the AVP to capture some trajectories to use to refine a Groot model? And I think that's a great, I would love to, it's on my list, but there's a lot on my list.
Yeah.
Of interesting things to learn, right?
Uh-huh. Yeah, and I think they're going to release a class similar to that at GTC, at the Paris GTC as well. So stay tuned for the classes there too.
Yeah.
Separate encoders.
I imagine this goes back to the different input-output types that we have while we're talking about policies.
Yes.
So deployment, yeah.
Yeah. So separate encoders. So are you so for this? I assume you're talking about different actuator types in Isaac Lab, right? So for that one,
sensor types, yep.
Or sensor.
Sensor, yeah.
Oh, sensor types. Okay. For Isaac Sim, in terms of joint state, we're just giving you ground truth data, so there's no additional noise given there. But you can always add your noise yourself to make it mimic the particular robot encoder that you're trying to you're using.
Well, I think that's the crux, right? For a lot of us, is that in Isaac Lab, when you train, you have direct access to ground truth, anything you want. Mm-hmm. And it's a lot easier to train a robot to do things if you know everything.
Yeah. Exactly.
And with complete correctness.
Mm-hmm.
But in the real world, you only have access to whatever sensors you might not even have access to joint position. I don't know if you typically do or not.
Or the joint position you access might have an error in it that you had to correct for.
And so that's why this Isaac Sim deployment is so important, is because it's the bridge where you can start with that perfect state data and with the APIs that Stephen mentioned. And then over time, you can say, okay, well, now we're going to introduce ROS, we're going to introduce latency, we're going to have imperfect joint positions, and you can start to intentionally make your observations more and more similar to what you will get in the real world. And you can
Mhm.
craft that so you start with this idealistic policy, and using Isaac Sim, you can turn that into a realistic policy.
That's right.
So I see another question. I can take this one. Question is, what are other tricks of sim to real deployment through NVIDIA Isaac and Omniverse libraries other than domain randomization? So a quick one, like domain randomization is when you actually change visual features, photorealism within Omniverse, and you can generate very realistic scenarios where robots will be running. So that's the first way. Another way is doing hardware in the loop or software in the loop testing. So in that case, what you're doing is essentially you're running your software that you want to test on either the same computer on another system also, like an edge device, and you test Isaac Sim as the environment the software is running in. So it's kind of like testing in the real world is dangerous, so you do it in Sim, but then you can get fairly robust behavior in Sim and then be sure that it'll behave very closely in the real world. So that's software in the loop is another trick. Hardware in the loop is same concept, but you're actually running it on the target hardware. So that's a very similar trick. And then, of course, there's something that we covered today, imitation learning. So imitation learning is when that's more of the layer on top, which is Isaac Lab. So in imitation learning, you're actually showing the robot how to do something, and then it learns based off of that demonstration. So all of these are different ways to achieve robust robot behavior when you're actually deploying the real world. That was a good question, a general, I would suppose, Isaac Sim related question. I think we have a couple of more minutes maybe. So let me pull up some more questions we could take in that time. Stephen, Eric, would you know about this one?
Is it feasible to have real-time signal externally? If so, what's the minimum time sample for? Okay, that's a question I think we had to follow up on the forum. I think there's a way to run, well, not quite real time, but you could always have Isaac Sim publish a clock, and then have your policy, your ROS policy run with that clock. So from the policy perspective, it's running at real time, but from your perspective, it's not exactly real time. But other than that, we will probably have to follow up with this question offline.
Well, and I might just say that if you're in that ROS 2 world, then they're really you can do just about whatever you want with Python.
Yeah.
I mean, sky's kind of the limit.
Mm-hmm.
There's this like 2 or 3 questions towards the end. I think we can answer these.
Mm-hmm.
When deploying from Isaac Lab to Isaac Sim without applying empirical normalization to the observation values, does the deployment work properly? Is this something anyone has tried? I haven't tried this.
Not quite. But I think because Isaac Lab and Isaac Sim, they run on the same physics engine right now. So if your environment is exactly the same, then the observation you get from Isaac Lab should be exactly the same as the observation you get from Isaac Sim. So in that case, from your policy perspective, they really shouldn't see anything different just because it's running from lab and now it's running on Sim. But I think this is something you have to experiment.
Well, and I was going to say too that I think you probably have a harder time once you go from Sim to real with this kind of thing. And what I would recommend there is it's going to be easier to fix your configuration in Isaac Lab than to fix your real robot. So when you get to this point, look at your real robot and figure out, how it should be normalized, and then go back and retrain in Isaac Lab with kind of normalizations and actuator properties that match your real robot as closely as you can.
And I think this question is something we could also follow up on the forum because there seems to be an issue with deployment because it's not working correctly. So we may need to see some logs or something to actually get down to the actual issue here. Yeah, forum would be the right place to go.
Yeah, it seems like they're having specific trouble.
Mm-hmm.
It's been fantastic. You guys have done an amazing job, all of you, covering a lot of information and answering a lot of great questions. I want to also let everybody know who's watching and participating. Thank you first. But second, it doesn't stop when this live stream ends. They've continued the conversation. They've already mentioned that Isaac Sim support is handled on the NVIDIA forums. We posted those links in the chat. Isaac Lab is supported via the Isaac Lab GitHub page. Very different places, but important you go to the right place for the right thing. And then obviously, if you want to continue the questions, which are fantastic, that are coming in right now, we can't get to all of them. Just go to the live streams channel we set up on the Discord server. We've got a link to this replay. We're going to be posting Stephen's great presentation deck in a few minutes, so that will be there. I often see sometimes people will post questions and they drop it and they leave it, and you shouldn't do that. Just go right to Discord server, go right to the live stream channel. And for people who are new to Discord, really quick tip. There's a search bar right at the top right where you can search any word, any keyword, any person. It'll tell you exactly where to go. So just type in live streams. If you have a hard time finding the channel, it'll bring you right there. And there you go. My producer has just putting a nice banner here. We have an Isaac Sim, Isaac Lab office hour happening in 20 minutes, 24 minutes from now. So if you're watching this live, in just a few minutes, we're going to have the Isaac Sim, Isaac Lab office hours, which Eric and many great members of the community, Scott Dempsey, one of the ambassadors, regular, Muramar Bay from Lychee AI, just a great group of people hanging out and discussing Isaac Sim and Isaac Lab. So it's kind of like part 2 of this office hours. Highly recommend you.
And we usually just like talk to each other and try to kind of decompress and process and figure and help each other understand what we talked about on this live stream.
It's great, and you get to meet some really fantastic developers doing really cool work. So highly recommend. So go to Discord afterwards for either questions on this live stream or go to the office hours to say hi to everybody. If you're shy, don't worry about it. You just hang out and listen. There's also a little text channel, so you can type your stuff. You don't have to show your camera or anything. Anyway, the other couple things I want to just remind everybody, GTC Paris next week, we have that community discount code. Although if you have a Viva Tech Pass, you're in for free. But the GTC Pass for Paris is actually very affordable. It's very inexpensive. But we do have a discount code for that as well. We posted that in the chat. We'll post it again. That's happening next week. Be sure to watch the keynote with Jensen. That's going to be amazing. You can watch that no matter where you are in the world, or watch the replay the next day if it's too late for you. And the week following next week, we have the Le Robot Worldwide Hackathon happening, celebrating the Robot SO 101, which I know everybody's a big fan of, including Eric here. So highly recommend you jump into these things. And also, if you happen to be if you're watching and you're in Montreal area or you know some Montreal, there's a really fun, exciting event happening tonight. Wow, there's so much action happening everywhere. At the Moment Factory studio, they're hosting a great mixer revolving around OpenUSD with some great speakers and a great crowd. We've posted the details for that on the Discord server in the events area. So ping me if you need help. You can always reach me by going to edmar.net. It'll bring you right to my LinkedIn page, and you can message me there. But our Discord server has this event on there. That's happening tonight, I think starting at 6:30. So lots of good action. Before we say goodbye to everybody, any last words from any of our panelists here? I think we covered a lot of ground. Steve, you did a fantastic job. Sorry, fantastic. Sean, thank you for all your great support. Do you guys want to give any last words of advice, though, before we sign off?
Yeah, thanks, everyone, for joining. It was great. And thanks for all the questions, as usual. And let's keep this discussion going on the forum on Discord so that we make sure we can answer everything. These are very complex topics, of course. So like the aim from our side is just to make it easier for you guys. And we hope everyone gets a chance to try everything out.
Awesome. There it is. The legend himself, Lychee AI, jumping in to the last second. Robotics Club also. Great. Thank you so much, everybody. Really appreciate everybody coming on. Wow, all these great comments. Thank you, everybody. All right, so we'll see you. Hopefully, for some of you, we'll see the Isaac Lab, Isaac Sim, Isaac Lab study group happening in a few minutes. Otherwise, we'll see you on the forums. We'll see you on Discord. Have a great rest of the week, everybody. Thank you.
Thank you
for inviting me. Thank you.